Hi Chemistry, Unit 3, Chemistry and Society, revision video. Collision theory is much the same as in Nat 5. You need to understand the ideas at cost if a reaction is too slow, and safety if a reaction is too fast. And you need to understand that the reaction occurs when we reach something called activation energy. Calculation average rate is the usual way of change in product divided by change in time, but you also need to understand that you can find the relative rate of reaction by 1 over T. This is where you've got several investigations and you want to consider how different temperatures or concentrations affect a reaction. As with Nat 5, concentration, temperature, catalyst and particle size all affect the reaction. This time we also got to consider pressure, which is effectively the same as concentration. Activation energy is usually defined as the energy required for a reaction to occur, and it's given the symbols EA. And an activation complex is where the compound of reactants and products is formed at the activation energy. This could fall either way, back to reactants or onto products if the energy is not correct. Pressure increases the reaction rate, like I said, by the same as concentration because the particles are closer together. So effectively it's like concentration. Catalysts can effectively come in two flavours. They can be homogeneous, i.e. in the same state as the reactant, or they can be heterogeneous, which will be in a different state as the reactant. And it lowers the activation energy that's required. They're not used up in the reaction, and they will form bonds with the reactants. As far as decreasing particle size, that increases surface area, as shown, and same with increasing concentration, increases the number of particles there that's got the correct activation energy, so faster reaction. Temperature is a measure of the kinetic energy that the particles have, and obviously the faster the energy, the more particles above the activation energy is going to be available for a reaction. As you can see with the two energy distribution diagrams, to increase the temperature, you lower the height of the curve, but extend it to the right, so increasing the number of particles available for a reaction. If you look at the energy diagram for the catalyst, then you're reducing the EA, activation energy, so that's again why the reason there's more particles above the activation energy, more particles available for a successful collision. This can be seen from the two rate of reaction graphs. If we increase the concentration, then we proportionally increase the reaction rate. Double the concentration, double the reaction rate. Whereas if we increase the temperature, then we increase the reaction rate a lot faster. Okay? To find the time, often we are asked to look up the time taken for a reaction at a certain concentration or time, and do it as we've put on the lines on there. Just inverse the formula, reaction rate equals 1 over time, to time equals 1 over reaction rate. As can be seen here with the energy diagrams, we have reactants going to products. If the reactants have more energy than what the products will have, then this will be exothermic. It will give out heat. It will be negative as far as the energy is concerned. Whereas if the reactants have less energy than what the products will have, the products have picked up energy from somewhere, they will therefore be positive. A catalyst alters the activation energy that's required, but does not alter the change in energy between the reactants and the products. As stated earlier, industrial chemistry is about making profit, so you want to make sure that the things react as fast as possible while being safe. You don't want the reactions to run away. The same with being too slow, you want to make as much money as possible. The definition of enthalpy of combustion is when 1 mole of a substance is completely burned in oxygen. To find enthalpies of combustion, solution, formation, all these sort of things, it's the same formula. EH equals Cm delta T, as we've used it in Nat 5. The difference will be this time you'll be expected to be able to work it out per gram, and per mole. These are shown on the sheet. Hess's law states that for any reaction, the change in enthalpy of the reaction is the same no matter how the reaction is done, or the route taken. As you can see here, with the second box, I personally prefer the equation way of working these things out, where you have to look at matching the equation to the one that's given the target equation. This is done by doubling up if need be, or reversing if need be, other equations of combustion. Bond enthalpies are the energy required to make and break bonds. These are given in the data book. And what you have to do is match up, find out the number of bonds being broken on each side of the equation, and then take away the products from the reactants. Again, if it's a negative figure, it will be an exothermic reaction. If it's a positive figure, it will be an endothermic reaction. For any system at equilibrium, then the rates of the forward and reverse reaction will be equal, the same going in as the same being remade. But the concentrations of the reactants and products will be stable, but not necessarily equal. Le Chatelier's principle is that changing the conditions at equilibrium will shift the reaction to the side to remove that change in the conditions. As can be seen in the lower left-hand box, if we add sulfuric acid, we're actually adding H plus ions. This means we're increasing the concentration of H plus ions, so the reaction will be pushed back to the left to get rid of those H plus ions. If a reaction is exothermic and we heat it up, then to try and get rid of the extra heat, the reaction will push to the left, i.e. generating more reactants. Whereas if a reaction is endothermic and we heat it up, then it will try and generate more heat, so it would push to the right, with increasing the amount of products being made. Pressure also works on a similar idea. If we have a reaction where there's 3 lots of pressure on one side, 3 moles of gas, and only 2 moles of gas on the other, then increasing the pressure will force the production of the 2 moles of the product, whereas decreasing the pressure would force the production of the reactants, if there are more moles of it. We'll now start thinking about chemical calculations. Now, one of the things that you first need to remember is we're looking generally to find the number of moles, and the number of moles relates to all 3 of the type of calculations that you'll finish up doing. If we have the question and they've got mass mentioned, then you're going to be using the blue triangle to find the number of moles. If we've got the question mentions concentration or volume and we're talking liquids, then we're going to be using the orange one. And if we're talking gas volumes, or it gives you a molar volume, then you're going to be using the purple one. In higher chemical calculations, you'll generally be given 2 pieces of information about one of the reactants and only one about the second. The idea is that you find the number of moles for the first one, then put that into the second one so you can find concentration or volume. Don't forget, you've got to remember that you may have to adjust your number of moles for the second substance by whatever ratio is given in the equation that you're working to. The following sheet gives you examples of limiting reagent, or sometimes this is which is in excess, percentage yield, atom economy, and molar volume calculations, and how to do them, how to lay them out. Remember to give your working out. Even if you make a mistake and your answer is going to be wrong, there are marks available for showing the right progression through the actual equations. Last but not least is chemical analysis. This way you'll be asked about chemical processes that you should have come across. Standard one is chromatography. Things like the mobile phase, the stationary phase, and how these are affected by polarity and mass of the actual molecule that's moving. How to work out the RF value, again an example is given. There are things you need to think about with gas chromatography. Often you're given examples of gas chromatography and asked to use that with various ideas as to what is present, how much of things that are present. If there is too much of the substance, then you can have problems with it not fitting into the actual gas chromatography itself. So you dilute the sample by a known amount. And you need to be able to work out things like standard solutions and how to work them out. The last thing are redox titrations. In these, it's the same idea as a normal acid-base volumetric titration, but you're looking to compare two separate equations whereby you're using information from one in the other. Again, this comes down to look for the two pieces of information you're given about one of the chemicals. Use that to find the number of moles so you can find the concentration or volume of the second chemical, and look out for the ratios that these chemicals are put together in.